Okay, hello, welcome to the New York City Category Theory Seminar, December 9th, 2020. Dan Shiebler will be speaking from Oxford, titled Functorial, Manifold, Learning, and Overlapping Clustering. Last year you spoke about formal language theory, monoidal grammars, and stuff like that. It's totally different.
Yep.
Good. I like that stuff also, but this is nice. Dan, can you start off? Can you start off telling us something about you, where you went to school, and where you did your degree, and stuff like that? Okay,
yep.
Go for it.
Okay, so hi, I'm Dan. I'm a PhD student at University of Oxford. I did my undergrad at Brown. I also work at Twitter, and doing stuff that's completely unrelated to category theory. So the focus of my research is on the intersection of category theory and machine learning. I'm trying to explore each of the different intersection points. What I've currently been digging deep into the intersection around unsupervised learning, especially the ways that's unsupervised learning and the sorts of structure preservation maps that exist in different unsupervised learning algorithms can be modeled with category theory. So there's a lot of interesting research out there that already exists on this, and so this is my attempt to build on it and dive deeper. So today I'm going to be presenting work that's currently, it's in submission at the Algorithmic Learning Theory Conference. Fingers are crossed that it'll get accepted, but we'll see. The title is Functorial, Manifold Learning, and Overlapping Clustering. This is really a exploration of clustering and manifold learning from the perspective of category theory. There's not that much heavy category theory, really. The main thing that I explore is functoriality. I tried to minimize the amount of really intense technical details of more sophisticated categorical subjects, and really tried to limit to this ways that we can use functoriality and ideally in the future naturality as well to explore the structure preservation present in different kinds of algorithms. So I'm going to just jump in. So basically in unsupervised learning, in this kind of perspective in this framework, we operate over a metric space that we assume has been drawn from some larger space according to some probability distribution. And we aim to determine as much information as we can about this generating distribution from the metric space that we observe. And in order to do this, we make lots of assumptions about what that probability measure might be like. And we try to infer things based on these assumptions and based on the structure that we observe in the metric space. So three classes of unsupervised learning that are particularly common are density estimation, where we just directly estimate the probability measure, which I'm not really going to be talking about today. There's clustering techniques, which attempt to group points in our data set and our finite metric space that we observe together. These groups can be interpreted in a couple of different ways. They could be regions of high density in our in the support of this probability measure, or they might be path components. They could also be regions of attraction. Manifold learning algorithms construct embeddings for the points, which we interpret as coordinates for this support. So if we assume that there's some low dimensional manifold upon which we can represent our points in, the goal of manifold learning is to find that. Functoriality is useful for studying unsupervised learning, primarily because we can study the invariances that algorithms preserve, which tells us a lot about how their operation and structure relates to the kinds of insights that they're attempting to derive. This allows us to determine the similarities and hierarchies of algorithms based on the categories they're functorial over, or to derive new algorithms that satisfy different sorts of constraints. that we build from a functorial perspective. I would say that the functoriality perspective is one of identifying inspiration as opposed to something that's more rote and direct. So I'll begin by talking a little bit about the way that we're going to represent structure and data. So I'm working with Uber metric spaces here, really just because it's useful to have an infinity. It's really just a metric space with infinity and a little bit less requirements on identifying points that have the same distance. So you can have 2 points that have 0 distance that are not the same point, and you can have infinity distances. So a natural notion of morphisms between finite metric spaces is non-expansive maps. So these are basically maps where we don't allow the distance of the target of the morphism to be larger than the distance of the domain. So we have, they're essentially just functions that they're not quite isometries because the distances can get smaller, but distances can't get larger. So there's sort of a hierarchy of categories here, which we'll go back to a couple of times. There's the one with the least structure, which is UMAP, where morphisms have non-expansive maps. There's UMAP inj and bij, where we restrict to injective and bijective maps respectively. And oh, this last one should be UMAP iso. Sorry, it's a typo, where morphisms are isometries. So isometry is distance preserving map, a distance preserving isomorphism. So that's the most structure. And so these are in a containing relationship. Each one contains each one is contained by the one above it. So in this work, I use simplicial complexes. We use a category of simplicial complexes, and the primary purpose of them is to have a nice way to arrange data and to have useful ways to represent how different points are close to other points. This is really useful later on for clustering and also for manifold learning. The simplicial complex perspective has been, there's sort of a ton of different perspectives on the relationship between simplicial complexes and metric spaces and clusters. Some work by Carlson, then also the UMAP work by Leyland McInnes. Some works focus on simplicial sets, primarily because they're easier to represent categorically. There's a lot more interesting things that you can say about them in perspective of their functorial relationships and the kinds of additional things that you can do. However, we focus on simplicial complexes here because the presence of degenerate simplicial maps and degenerate simplices makes things a little bit more difficult with some of the adjunction relationships that I want later on. And also the additional complexity of simplicial sets is not necessarily warranted here. So that's sort of the motivation behind sticking to simplicial complexes. So basically a simplicial complex, it's one of those things where if you haven't worked with them in the past, they're impossible to understand. So I'm not going to talk about them in extreme detail, but essentially you could visualize them as these geometric shapes, but they're also more explicitly a family of finite sets that's closed under taking subsets. So one simplex is a point, a zero simplex is a point, a one simplex is 2 vertices connected by an edge, a 3 simplex is a triangle, etc. So a simplicial map is a vertex map between simplices that obeys somewhat like something like an injection. You're essentially taking it's not necessarily injective though, you take the vertices of one, map it to the vertices of another within a simplicial complex. And the map is a simplicial map if the image of each of the simplices in your domain simplicial complex forms a simplex in your target simplicial complex. So this is essentially the natural notion of morphisms between simplicial complexes. So our category of simplicial complexes, which I'm representing as SCPX, has finite simplicial complexes as objects and simplicial maps as morphisms. So a pretty common idea is to define a functor where we take a metric space to a complex whose simplices are the sets where the distance between any 2 points in the simplices are the sets of points in the metric space whose pairwise distances are all less than delta. So this is related to the Rips complex. And I think it is exactly the Rips complex. And this requires a fixed choice of delta. So this sort of harkens to a common notion in topological data analysis of how do we then represent this kind of structure across multiple scales, which is we utilize a fuzzy simplicial complex. So this is very similar to the fuzzy simplicial sets that David Spivak has written about and Lena McGinnis utilizes in the UMAP paper. These are essentially just we represent them with a functor, but they're really just a series of simplicial complexes that each exist at different scales. So the functor that we utilize here is, so this IOP, I is here just the poset of 0, 1. So we have for this functor is just representing the data of simplices that exist in at different scales, at different degrees of an index. So near 0, we have our largest simplex, and near 1, we have our our largest simplicial complex, and near 1, we have our smallest simplicial complex, where for the simplicial complex that's indexed by 0.3 is going to have a simplicial map into the simplicial complex that's indexed by 0.7, for instance. So this is this fuzzy simplicial complex. The idea is that each simplex in the simplicial complex exists with a different amount of confidence. The ones that exist all the way near 1 are the ones that are really certainly in the simplex, really strongly in the simplex. The ones that exist only up to like 0.1 or only up to 0.05 exist with less confidence or less certainty. So the sort of highest number in the 0, 1 range is the strength of the simplex. The morphisms in the category of fibered fuzzy simplicial complexes are natural transformations. So these are really just a collection of simplicial maps that exist at each of the different scales. So the point of all of this simplicial complex stuff is really just to be able to define this functor, which is our finite singular set functor, where that maps a metric space into this category of fibered fuzzy simplicial complexes. So a given metric space is mapped to the fibered fuzzy simplicial complexes whose simplices at the strength A are these sets whose the pairwise distance of every point of the set is less than this sort of transformed distance threshold. So we utilize negative log. It looks random, but it's really just because it's a convenient contravariant transformation from 0, 1 to 0 to infinity. That's really the only reason why we use it. And so that allows us to transform these slight differences in strength to differences in distance. So intuitively here, fencing is taking a metric space and forming lots of collections of points that are in sort of arranged in this hierarchical fashion, where points that are closer together in the metric space exist at higher strengths, closer to 1 on this 0 to 1 scale. Points that are farther away don't exist in the same simplex until we're closer to 0. They only exist together with less strength. So this sort of notion of collections of points that are arranged in this sort of fuzzy geometric structure is a nice thing to build clustering algorithms on top of, which I'll now talk about. So kind of taking a step back from very technical to very kind of more motivation focused. Clustering is, like I said earlier, you could think about it in terms of path components of the support of the generating probability measure, or you could think about it in terms of a like much simpler concept. You have data, you have a bunch of points in that data. You're trying to find collections of points that share some common trait. And a clustering algorithm is going to accept a finite metric space. It's going to assign each point in that space to a cluster. Assuming there are data sets that we're representing with a finite metric space, assign each point in the space to a cluster. So there's two main ways to do clustering. The most common way is non-overlapping clustering, where we basically form a partition of the space. Another way to do clustering is overlapping clustering, where we form a cover of the space, and each point may end up in multiple clusters in the cover. One of the benefits of overlapping clustering is that we don't necessarily need to have points that are in an intermediate space bridge points that are farther away from each other. So basically, if we have a situation like this, where we have this sort of two natural clusters and a couple of points that are connecting them, one thing that a non-overlapping clustering might do is say that, well, there's a path between these 2 points, and so we should connect them. Whereas it may also say that there's not enough density between these 2 points, so we should completely ignore this chain and separate these into 2 separate clusters. An overlapping clustering algorithm can add the points in the chain to each of the 2 dense clusters without necessarily joining them, because some of those intermediate points can be both in the left cluster and the right cluster. So that's sort of one of the reasons why overlapping clustering can give us a little bit more information about the space and preserve more info. In practice, usually non-overlapping clustering is much more useful for a couple of reasons that I'm not going to get into. But we're going to utilize overlapping clustering because it makes it a little easier to transition to manifold learning. There's also a lot of this, the mathematics of how simplicial complexes and functorial overlapping clusters are related has already been studied pretty thoroughly by Culbertson and a few others. And the main contribution of this work is taking that, reformulating some of the details of the simplicial complex foundations, and then adding all of the manifold learning stuff on top of it, which I'll talk about it in a moment. So this is still sort of everything I've talked to up until now, and for the rest of this clustering section, is mainly reformulations of existing ideas. The manifold learning is the main novel component. So the kinds of overlapping clusterings that we're going to focus on are this notion of non-nested flag covers, which is basically a cover of data that behaves nicely, where we don't have like two clusters that contain each other. We also have that the simplicial complex that corresponds to our flag cover is a flag complex, which means that its simplices are the cliques of a graph, but that's not, it's more of a technical detail and not tremendously important for sort of fundamentally understanding what's going on here. But basically, these are sort of a well-behaved cover of our data set that's transitions nicely to a kind of simplicial complex. So we can form a category of these non-nested flag covers, which we call cov. And the morphisms in our category of non-nested flag covers are refinement preserving functions. So this is basically just functions on the underlying data sets that have this refinement preserving property. We have that the set in the image of any set must also be a set in the cover of the image of the data set, the image of the function. So these are very similar to the notion of non-expansive maps when you kind of think about what FinSing is doing, and the notion of close togetherness in the source implies close togetherness in the target. The non-expansive maps, we're taking 2 points and mapping them such that the image of those 2 points must be closer together than the 2 points that are getting mapped. Here we're mapping points such that if the points are grouped together in our source, they must be grouped together in the target. And so these are related functorially, obviously. And so that's sort of the point here. So there's a couple of transformations between cov and SCPX. These are some of, we can utilize these to build clustering algorithms from some of the functors that I'll describe in a second. So since the maximal simplices of a simplicial complex form a non-nested cover, we have this functor flag that takes the maximal simplices. We can also take the connected components of a simplicial complex. And so that's another way to cover a data set. Note that the maximal simplices will intersect with each other. Their intersection property is exactly what makes the simplicial complex flag. Whereas the connected components of the simplicial complex will not intersect with each other. The subsets of a non-nested flag cover form a simplicial complex, as I mentioned earlier. So this allows us to have this other functor that maps from cov to SCPX that sort of goes in the opposite direction. And there's some adjunctions here, but I'll leave them out for the moment. So this now is sort of our get to the meat of this, where we can define clustering functors as functors from subcategories of UMAP to cov. And this sort of clustering functor now is taking these non-expansive maps that we were mentioning a moment ago and mapping them to refinement preserving maps. And there's different types of clustering functors based on the category that they are functorial over. I'll talk about this more in a moment, but if you'll recall, we talked about subcategories of UMAP that had injective maps or bijective maps. There are certain clustering algorithms that by the types of structure that they utilize are only functorial when the source category has injective maps, or only functorial when the source category has bijective maps. This allows us to form hierarchies of clustering algorithms, which is one of the nice and interesting aspects of this line of work, is this ability to group together algorithms based on this sort of functoriality. So we can form hierarchical clustering algorithms utilizing a very similar notion as what we discussed earlier for fuzzy simplicial complexes. Basically, a hierarchical clustering algorithm is a functor that maps into a hierarchical clustering is a functor in this category fcov. So this is basically a series of covers that each contain each other, indexed by this number in 0, 1. This is very similar to the notion of fuzzy simplicial complexes that I mentioned a moment ago. It's almost identical, except rather than having simplicial complexes with simplicial maps between them, and we instead have these covers with refinement preserving maps between them. A hierarchical clustering functor is now a functor that maps this subcategory of UMAP to our category of hierarchical clusterings, or FCOV. And the characterization of these functors is that at each level, at any fixed A, it collapses back to a flat clustering functor. So this now allows us to have functors that might apply a different threshold cutoff, for instance, between points before it might group them together. You might think of a clustering functor that only will group together points into the same cluster if their distance between each other is less than some thresholds. Then the hierarchical version of that would be that functor at each possible distance threshold. And so that would then produce a hierarchical clustering, which is a map from these distance thresholds to clusters. And so this all sort of flows together in a functorial framework, from metric spaces to hierarchical clusterings, which are indexed as maps from this index set 0 to 1 to our category of covers. So two examples of this kind of clustering algorithm are maximal and single linkage. So we can now go back to our Fidenstine functor, which is are really just the RIPS complex building functor that maps it's a finite singular set functor. It maps a metric space to the simplicial complex formed where each simplex has a distance that's based on the distance threshold that's based on the indexing set. So the maximum linkage clustering functor applies our flag functor, which, if you'll recall, maps to the maximal simplices, whereas the single linkage clustering functor maps to the connected components of our RIPS complex. So sort of in other terms, maximal linkage forms the maximal simplices of the RIPS complex, whereas single linkage clusters based on the connected components of the RIPS complex. And in terms of what's actually happening here, if we say we have these 5 points where 0, 1, and 2 are all very close to each other. 2 is close to 4, but 4 is far from 0 and 1, and 3 is far away from everything else. Well, in both maximal linkage and single linkage, 0, 1, and 2 are going to be in the same cluster because they're all close together. However, 4 in maximal linkage will only be grouped together with 2 because the maximal simplex that 4 is a member of is the simplex that the one simplex that it forms with 2. In sort of other terms, they're only together if their distance is less than some thresholds in maximal linkage. However, in single linkage, since we're taking connected components, we work based on paths. There's a path from 4 to 0, where each step in the path is traversing a distance that's less than our threshold. So 4 and 0 are in the same complex, or in the same cluster. And so this is sort of the difference between these two strategies of clustering points. So the one nice thing that we can say about this is that any hierarchical clustering functor lies in a spectrum between maximal and single linkage. So up to a rescaling factor. For any clustering functor, there's a rescaling factor at which maximal linkage refines it, and the same rescaling factor, at the same rescaling factor, that clustering functor refines single linkage. So this is a nice way of organizing clustering functors in terms of their relationship between, the relationship or place in the spectrum between the most severe strategy, which is only putting 2 points together if they are themselves close together, or the most loose strategy, which is putting 2 points together if there's any way to connect one to the other, and everything else falls somewhere in between that.
Dan, could you back up for one slide?
Yes.
This 2 in the top picture, it's a member of both clusters. Is that the point?
That's correct. Yes.
So it's like fuzzily part of one cluster, and it's fuzzily part of the other cluster. Is that possible in the lower picture also? Can you have one thing that's part of 2 different clusters? Is that possible?
So in the perspective of both of these are mapping into the same space, and then the sort of the rules of that space, or that overlapping clustering, is permitted. But single linkage, because it is utilizing connected components, will never produce overlapping clusters. Right. The connected components functor will always produce a partition rather than a cover.
Like an equivalence relation rather than a partial order or something like that. The partition, fine. Partition is another way of saying it.
Yeah, equivalence relation.
Right. Okay, thank you. Sorry. Okay.
No worries.
Back to reality.
Cool. Okay, so now manifold learning, which is sort of the new, more novel part of this work.
And I think many people know what clustering is. I don't think most people know what manifold learning is. So go slowly with us.
Yes, totally.
Okay, we're virgins. Go on.
I will do my best. So intuitively, manifold learning in practice is sort of similar to just embedding algorithms. Kind of, you have your data, you have your metric space. You want to find embeddings in RD. You want to find some Euclidean embeddings that somehow represent your original data. Sort of the most fundamental of this is to preserve pairwise distances. I'll show exactly what that means in a second, between the points in our metric space with the points in our low dimensional embedding space. But there's a lot of different kinds of manifold learning algorithms that try to preserve different aspects of the higher level space in the reduced space. So the general idea is that given a metric space with n points, we want to find a nxm real valued matrix. I realize I've utilized both D and M here, but they're actually the same. That's what I get for editing this slide earlier today. Basically, we're trying to find m dimensional embeddings for each point in our original space that satisfies some property. And a concrete example of what that property might be is given by the metric multidimensional scaling algorithm, which is a particular manifold learning algorithm. Principal components analysis, which you may have heard of, is a special case of metric multidimensional scaling, under which we make a certain assumption about our input data. And the goal here basically is just to find these Euclidean embeddings such that the average, the sum of the squared distances between our metric space distances and our Euclidean distances in this embedding space is minimized. And so that this is like a search problem in the space of n by m matrices that is parameterized by our metric space. I don't know if anyone has any questions.
Wait, so just to be sure, the x sub 1 through x sub n are to be interpreted as m vectors, m as in manual?
We're going to find m vectors for each of these points. Right now, when they're given to us, there's no structure. They're just like points, and we have their pairwise distances because that's all we have to start is just a metric space. But we want to find these m vectors for each point such that the pairwise Euclidean distances on each of these m vectors is as close as possible to the distances in the metric space that we were given.
I see, thanks.
So what's often happens in manifold learning is this is sort of the most extreme case where we want to do an exact replication of our higher level distances. What's often the case is that we have some assumptions such that smaller distances are more reliable than larger distances, or there's some distances are likely to be very wrong or corrupted, or some other sets of priors on what we think about when we interpret the distances. And each different manifold learning optimization problem or each manifold learning algorithm makes a different set of assumptions around what kinds of structure in the original space are most important to preserve, and then utilizes that structure when it constructs an optimization algorithm that we will utilize to actually solve this problem.
And so, sorry, just one more question.
Yeah.
Is n the size of the finite set X, and then m is the desired dimension of the space we want to embed into?
That's correct, yes.
Okay, thanks.
Yeah, exactly. So in a manifold learning optimization problem, we can sort of represent it in terms of two components. One is a loss function, essentially, that accepts our n embeddings in Rm, or accepts an element of mat nm, and outputs a real value, or infinity, because we're using infinity here sometimes. And then also a set of constraints. Many manifold learning algorithms are constrained optimization, where there's either trying to find orthogonal embeddings or some set of other restrictions on how we want our final embeddings to look. And then our manifold learning optimization problem is a pretty familiar form. Just find the matrix that minimizes this loss subject to some set of constraints. And sometimes there's multiple matrices. This is not always a unique specification of the problem. But from the perspective of how we're going to be studying this, that's not tremendously important. So when I first started this work, I tried to focus a lot on what kinds of spaces are actually learned and what ways are the algorithms, what are the different kinds of matrices that can be formed or satisfy these optimization algorithms optimally based on different algorithms and different sets of constraints. But there's a lot of approximation that happens, and in practice, when data sets get large and messy, these spaces get extremely complex. And while that's also a useful area of research, what I really focused on here was the form of the loss function. And I focused on the relationship between how this loss function is specified from the data, rather than how the actual embeddings get learned. So the functorial relationships that I studied between the different categories of metric spaces and categories of manifold learning optimization problems are not between the learned embeddings, but between the actual optimization problems themselves, which I build a category based off of. And sort of the elements of this category are these tuples, where I've broken out our loss function into two parts, an expansive term and a contractive term, which I'll describe some examples of what these could be in a second. But basically, this is a very simple category and structure. It's just a pre-order where we have these tuples of n, which is our dimension, LC and LE, which are our contractive loss and our expansive loss, and C, our set of constraints. And we have this ordering relationship based on a sort of simple loss satisfaction. The LC of the image is always less than the LC of the source, and inverse for LE. And concretely, this is just has a direct relationship to the optimization problem. So given such an object, we have a optimization problem that's just formed as the sum of LC plus LE. We need to break this out into two terms because it's very common in manifold learning algorithms for the loss to have a way where it gets larger when you're far away from certain points and smaller when you're far away from other points. Like you want to be far away from the points that are far, for a particular point in our metric space and the learned embedding for that point. We want that learned embedding to be far away from the embeddings of points that are not close to that point in the source space. And we want it to be, we want that distance to be small for the points that are close in the source space. And the exact relationship between these two, the degree to which these things are the case, varies based on the algorithm. And so a very simple optimization problem that really has nothing to do with manifold learning in particular, but is sort of would be an example of an element of an object in this category, is just to find the orthogonal matrix that minimizes the sum of squared distances between all of the rows in the data set, which I think is like a perfectly aligned set of points that surround a sphere. So the main component here is, unsurprisingly, manifold learning functors, which we're defining as functors that are, I'll give a little bit more detail on their definition in a second, but basically they're mapping metric spaces into manifold learning optimization problems. And in practice, these are going to find groupings of points and penalize learned embeddings that are in the same group from being too far apart. And I'll describe exactly what that means on the next slide. But the intuition here is that because we are taking our metric space, finding groups of points that are close together whose distances we want to preserve, and then forming a loss function that is trying to preserve those distances, we want our manifold learning functors to factor through hierarchical clustering. So this is sort of the core insight of this, is that we can represent manifold learning in terms of overlapping clustering. So basically, a manifold learning functor is the composition of two functors. One is a hierarchical clustering functor, and the other is a functor from our category of hierarchical clusterings into our category of manifold learning optimization problems. And there's a couple of slight things that we do to keep things from getting degenerate. Like, for example, insist that the second functor maps to a optimization problem where n is equal to the number of points. So we're learning exactly one embedding for each point in n. So since we have this compositional structure as the definition of manifold learning, we can apply some of the insights into functorial clustering to manifold learning as well. For example, we have a universality of manifold learning algorithms, where all manifold learning algorithms lie on the spectrum between the version of that algorithm that factors through maximal linkage and the version that factors through single linkage. And I'll talk a little bit later about how we can take a manifold learning algorithm that factors through maximal linkage and switch its underlying linkage to single linkage and get a new algorithm that's better for a different class of problems. And so this is sort of a general formula of recognizing a manifold learning algorithm in terms of these two components. And then we can try switching out the clustering back to maximal linkage, back to single linkage, and see how this changes the sorts of embeddings that are learned and what kinds of problems that might be better for. And so there's a couple of ways to do that. And I have some experimental results at the end describing that. So like clustering functors, there's a couple of papers that exist that describe clustering functors based on the kinds of morphisms in the source category. Some algorithms are only functorial over injections, some algorithms only functorial over bijections. And there's a couple of interesting insights that you can make around the number of functors that are functorial over different categories. And we can say a lot of similar things about manifold learning now that we have represented it in terms of clustering. So for example, in order to be functorial over the category of a UMAP isom of isometries, we simply need to have consistent results over isometry classes. So permuting the points can't change the manifold that's learned. Whereas to be functorial over UMAP bijection, we need to have that same property and then also have the loss decompose to two terms, one of which increases as distances increase and one of which decreases as distances increase. And then so the other more interesting is UMAP inj, where we have of these two components, one increases and one decreases when we add points into our metric space. And so I'll go through concrete examples of sort of well-known manifold learning algorithms that fall into each of these different categories. And there's one thing to notice that there's no general UMAP manifold learning functors because of sort of the way that we've defined the category of manifold learning optimization algorithms. So one pretty common, well-known algorithm in the manifold learning world is Laplacian Eigenmaps, where these are basically, there's a couple of different ways to formulate this algorithm. Unsurprisingly, the most common way is by forming a graph from our data and then finding Laplacian and then finding its eigenvectors. But that's not actually the way that I'm going to describe it here. That strategy is equivalent to minimizing a certain objective function, which is how I'm going to describe it. But basically, the goal here is we have a data set of points, our finite metric space. We want to ignore all the points that are far apart. If they're larger than some threshold away from each other, we totally ignore them. And for any pair of points that's below a threshold, we want to make our distance between these points as small as possible in our final space. And to prevent the embeddings from just being all collapsed to a single point, we apply an orthonormality constraint on the actual embeddings that we learn. So this looks like this, which is really loud and complicated and has lots of parts. But the exact details of this are not tremendously important. Basically, there's two pieces here. Everything in this blue box is our functor from our category cove of covers into our category of manifold learning optimization problems. Some interesting things to note is that LC, our contractive loss, is 0. We can do this and only have an expansive loss because we're not caring about points that are too far apart. We're not trying to push 2 points that are far apart in the original space far apart in the final space. All we care about is collapsing points that are close together. So that's why LE is defined and LC is not. And we set a constraint because we're trying to prevent all the points from being collapsed at the same point. So then the Laplacian Eigenmaps algorithm, which is sort of the algorithm that's like very commonly used, is the composition of this functor, which forms this optimization problem from a clustering with the maximal linkage functor. And so this is a sort of complete description of what the algorithm is doing based on this composition of one functorial clustering, one clustering functor and one functor from our category of clusterings to category of manifold learning optimization problems. Okay, so our metric multidimensional scaling algorithm, which we described a second ago as our canonical example of manifold learning. This simple algorithm where all we're trying to do is find embeddings that optimally approximate our original space. We can represent it in the same way. And the tricky part here is that we need to break down the loss into a contractive term and an expansive term. And that's really all that this is doing, is just there's no constraints, so C is always set to true. And we have a contractive term and an expansive term such that this falls nicely into our category of optimization problems. And like Laplacian Eigenmaps, the metric multidimensional scaling algorithm is then the composition of this functor a moment ago that forms this optimization from a set of clusters with maximal linkage. So the one thing that's interesting to note about MMDS, the metric multidimensional scaling, and Laplacian Eigenmaps is that Laplacian Eigenmaps is functorial over UMAP inj and fcov inj. It's a functorial over injective maps because there's no expansive term, and there's then no negative terms in our, there's no negative terms in LE, and there's no positive terms in LC because it's always 0. Whereas that's not the case for metric multidimensional scaling. So intuitively here, the relationship between being functorial over injective maps and functorial over bijective maps comes down to the types of structure that the algorithm is trying to preserve when it forms this optimization problem. For something like Laplacian Eigenmaps that's only trying to preserve this close together structure, it can be functorial over the category of injective maps, whereas that's not the case for an algorithm like MMDS that needs to preserve a finer grained kind of structure. It needs to actually focus on the exact distance ordering that's in the original space. So a way more complicated algorithm that I'm absolutely not going to go through is UMAP, which is one of the motivations for this work, actually. This is a very popular, pretty contemporary manifold learning algorithm that is based around rescaling metric spaces, forming simplicial complexes from those metric spaces, taking a fuzzy union of these simplicial complexes, mapping them back to mapping this fuzzy union down to groups of points, this sort of flag cover, and then building a loss function, this fuzzy cross entropy loss, and minimizing it. So in the paper, I sort of break these down into 5 functors. It's pretty natural relationship because the algorithm itself is actually expressed in terms of simplicial complexes and a fuzzy union of them, which we can represent with a colimit if we utilize the fuzzy simplicial complex category. And the first 4 steps forms a hierarchical clustering algorithm. The last step is a functor from our category of hierarchical clusterings to our category of manifold learning optimization problems. So this is an example of a UMAP isom hierarchical clustering. It's not even functorial over injective maps, only isometries. This is because the UMAP algorithm in its first step actually rescales distances based on a local metric space around each point. This is part of what makes the algorithm effective, is that in order to build these simplices in a way where the global structure is preserved and the kind of nerve theorem is approximately satisfied, we rescale the distances such that we can roughly approximate a uniform covering of our space with points that are not necessarily uniformly distributed. And in order to do that, we rescale the distances from each point by the distance from that point to its nearest neighbor. And so this local metric space construction at the beginning removes even functoriality over non-expansive maps and only functoriality over isometries. And we can still represent this, though, in the framework in which we have one component that forms these groupings of points, and then another component that forms a loss function from these groupings of points, which is the fuzzy cross entropy step. Okay, so I said I had some experimental results. I know a table that just has a whole bunch of numbers on it is not particularly useful, but I can try to give some intuition into what's happening here, and then why we're doing what we can kind of get out of this. Maybe it's easier to. Oh yes, these are a little out of order. So this is the one that is a little bit easier to start with. So, as I alluded to earlier, the functorial perspective on manifold learning, one nice thing that this gives us is that we can now represent our manifold learning algorithms in terms of 2 parts. One is this construction of the loss function, which is composed with our construction of groups of points. And this first step where we form groups of points is utilizing a hierarchical clustering functor, which lies in a spectrum between maximal linkage and single linkage. So a natural question here and a natural strategy is to try out swapping out this first step with a different kind of algorithm or a different option. So one example is in MMDS, where we have this composition of this MMDS functor with maximal linkage. We could try composing this instead with single linkage. And this is useful in certain situations. So for example, if we have I guess taking a step back, there's a couple of other kinds of these compositions that can be useful. There's sort of 2 ways to do this kind of composition. One is to say, well, this is now a new hyperparameter, and we can sort of try any set of combinations and see what sorts of performance we get when we swap out the fuzzy cross entropy loss on UMAP with the Laplacian Eigenmaps loss instead. And now we have local metric spaces and the Laplacian Eigenmaps objective. And I have a few experiments doing that, but I think that's a little bit less informative than a simulated data experiment to demonstrate exactly what sort of value this drives. So that's what I have here. So basically what we're doing is consider this situation where we have a DNA recombination task. Let me see if yeah, I don't have an explanation of it on a slide, unfortunately, but I can kind of describe essentially what's happening. So if we have a original sequence of DNA that goes through several mutations, at each step having some bases that might switch to other bases randomly, what this will do is it will produce a artifact, a sort of history of all of the mutations that this string of DNA has gone through. And if we then build if we utilize each of these different transformations, each of these different snapshots of the DNA as data that we observe in our metric space, and we then build embeddings based on this metric space. If we utilize maximal linkage, we will not group together the first and last point in this mutation sequence if it's gone through lots of mutations and its distance is now really far. But if we use single linkage, we'll recognize this path of data from start state to end state and recognize that this final state of the DNA sequence was from this first state, because there's a sequence of points that lies between the starting state and the end state. And when we actually train the manifold learning algorithm and plot out the points, we see that the learned embeddings are all very close together for the points in the same mutation list. They're points that are sort of all from the same original string of DNA for the single linkage modification of metric multidimensional scaling, whereas that's less the case in the maximal linkage situation. And if we look at the performance in terms of accuracy of assessing which of the original sequences a final DNA state belongs to, we get dramatically better accuracy when we utilize the single linkage version of metric multidimensional scaling than the maximal linkage version. All right, thank you, everybody.
Thank you very much.
Thank you.
It's the whole world. Thank you. And any questions? Fire away.
I was curious about one part in an earlier slide where I'm blanking on which one, but you specified a constraint for one of the loss functions that was like A transpose D A. Yeah, exactly. Yeah. So I think that you had mentioned in passing that this constraint is there because we don't want ultimately for every element in the set X to get collapsed into just one cluster. So yeah. Is it appropriate to interpret this A transpose DA equals I like a sort of near invertibility, like to say that A will be invertible, but kind of just up to similarity with that matrix D interceding? Or is it something else going on?
I mean, so this is so basically this comes from there's two ways you can look at this. One way is sort of the way that I presented this, which is we have a problem. That problem is we want to get all the points as close together, but we don't want to collapse them all to the same space. And there's two ways to do that. One is we can penalize points that are far apart in the original space to be close together. The other is to apply some sort of constraint to prevent them from all being pushed in the same space. And this is just the constraint that comes out. The other way to derive this is in terms of eigenvectors of Laplacian. So this ortho normality-ish constraint here is just like an eigenvectors constraint. So it's the sort of invertibility comes just from the fact that we have orthogonal matrices when we're dealing with eigenvectors.
Okay, I see. Thanks for clearing that up.
A question.
Any other questions?
I have a question.
Please.
So what happens if you, like the example that you showed in the end, you're basically like you're embedding something that kind of looks like a discrete space, right? In R3, I guess, or something like that. And it's discrete in the sense that like there are all these little clusters that you want all these points to be together. I guess my question is, what happens if you applied this composite with single linkage that you're applying, but to a space that has more like cohesion and it's like more continuous instead of being so discrete?
So I think the case in which we want to apply single linkage instead of maximal linkage is if we expect there to be two things that's the case. One is there's relatively little noise. So the points are separated enough, like our groups of points that we're interested in are far enough away from each other that they're unlikely to get erroneously joined. And there's ways that we can transform our space using like robustness maps to make that easier. And the other is that there's some sort of artifact that our data is going to leave behind. There's if we have a transformation that's being applied, or if we have a path, like for instance, if we are trying to track like the movements of vehicles, we'll have data from each sensor recording. So we'll have like the first sensor, the second sensor, the third sensor. There's sort of a sequence of data, each of which is naturally related to the one before and the one after. And in that sequential fashion, we have a bridge between our first and last point, which may otherwise be hard to interpret. So if the points in our data set can be naturally interpreted separately from each other, then this single linkage perspective makes less sense when building manifolds. But if there's this natural path between points that should be grouped together and should be considered part of the same structure, then it makes more sense to utilize a single linkage like formulation. And the maximal and single linkage, like I said, are like the opposite ends of the spectrum. There's a bunch of different strategies that lie between them.
Okay, thank you very much. Any other questions? Okay, so let's thank our speaker again. Next week is our last meeting of the season. Next week, Arthur Parzignet is speaking about entropy, quantum entropy, classical entropy. He's a former CUNY person, so we know him. Anyways, and you're all invited. And if you're not going to show up, have a wonderful holiday season and come next semester. And we have already 4 speakers lined up for next semester. It's a pleasure. Everybody all right?
Thanks again.
Thank you.
Okay. Take care, everybody. Good night. Thank you, Dan. I'm going to send you an email, where it's uploaded. Okay.
Great. Thank you.
Okay. Take care. 99.
Take care.